Gemino, now we're having the third talk of Andreas.
Oh, thank you once more, Joa. So today we are going to discuss, I would say, the simplest problem of electrodynamics, because we have electrostatics and then electrodynamics, but I will not talk about telegraphy, waves, nothing, just the simplest problem. So we all, even mathematicians, when we study, even in high school sometimes, we make this kind of calculations. Ohm's law, so we have a current here.
People ask for it's very hot. It's okay?
So we have a constant current. Then by the right-hand rule, we find that the magnetic field goes against the blackboard. Okay, suppose we have a positive charge moving away from the wire. So QV cross B, the force is upwards. Okay, QV cross B. Or suppose we have a circular loop. Again, by the right-hand rule, the magnetic field goes inside. If the charge moves to the right, the force goes up. Okay, QV cross B. So the hidden message, what happens when the charge is at rest? Relative to the wire or relative to the loop? What happens to the force? Zero. Okay, so that is, we all learn that even in high school sometimes, but in undergraduate in physics or mathematics, we all learn that. That's Lorentz law. And, but what I will talk today is just this problem with V equals to 0, okay? So this subject of another book of mine, The Electric Force of a Current. This book for the Germans, it has even been translated to German. In German it's called Elektrische Strom- und Oberflächenladungen, was Wilhelm Weber schon vor mehr als 150 Jahren wusste. Okay? So you can give a look, and this is the subject. Okay? All these books, even the German one, you can download from my homepage. So we have a steady current I flows in a wire of resistance R connect to a battery of EMF V. Consider an external charge Q at rest relative to the circuit. Simple questions I will ask. The whole subject today. Does the circuit exert a force on the stationary external charge? Does the wire generate an external electric field? Because the magnetic field I have shown here, but now I am asking electric field. Why generate an electric field? So, but that's a question. Is the wire neutral on all of its points? Because we know that there are charges inside the battery. But what about the other points of the wire? So, these are the questions. What is the force acting on this stationary charge? It is at rest. Does the wire generate an electric field, not magnetic field? And is the wire neutral or not? Okay? Very simple questions. I give some answers here. The first one by Maxwell in the treatise. He said the following: such an action has never been observed. Action between a force between a stationary current-carrying wire and a stationary charge. He said no such a force. Clausius, the same Clausius of thermodynamics, of the third law of thermodynamics, entropy and so on, he was fighting against Weber. He knew that with Weber there should be a force, even for a stationary charge. And Clausius said, there is no such a force. And then Clausius creates another electrodynamic force law, which is different from Weber, different from Lorentz. We don't learn that, but he devised an electrodynamics of his own. And his electrodynamics was based on this postulate. These are the words by Clausius in 1877, after the treatise from Maxwell. We accept as criterion the experimental result that a constant current in a stationary conductor exerts no force on stationary charge. Usually I call this Clausius postulate, okay? So he assumed this postulate to create his electrodynamics. He was fighting against Weber. So he utilized this explicit postulate. In Feynman's book, the Feynman Lectures on Physics, published in 1964, he has the following sentence in the middle of volume on electrodynamics. In a normal conductor, like copper, the electric currents come from the motion of some of the negative electrons, okay? Then he continues some calculations, then Feynman concludes. There is thus no electric field outside the wire. Only the magnetic field, but no electric field. This is Feynman. Jackson is the book which here in Brazil we utilize for PhD students in physics, in electrodynamics. Because in this case, the electrons, they are moving with constant velocity. But in this case, the electrons, they are accelerated, even for static currents, because there is centripetal acceleration. So we might think, okay, when the electrons, they are being accelerated due to the centripetal acceleration, they might emit radiation. And this radiation might act on a stationary charge on the outside. But then there is an exercise in Jackson's book in which he integrates that, not only for a circular loop, for a closed circuit of arbitrary form, shape. It's a complicated calculation, but it is an exercise in Jackson. That's the conclusion of Jackson. For a real circuit, the stationary positive ions in the conductors will produce an electric field which will just cancel that due to the moving electrons. Even taking into account the centripetal acceleration and the radiation it might produce in the outside. When you integrate this radiation for a static current, it goes to zero. Essentially, that's the conclusion of this exercise by Jackson. I will now quote a very curious book on mechanics. This book, I don't know why, this Skinner, he decided to discuss Weber's electrodynamics in a book on mechanics. Just in one page. Then he presents this picture here. This is a picture from this book. So there is an electric current flowing in this circuit, and there is a stationary, at the focus, at the center of the circuit, there is a stationary charge. Then this is what reads in the caption of this figure. A crucial test of Weber's force law. Because, as I said, for Weber, even if the charge were at rest, there should be a force. Then he says the following. According to Weber's force law, the current of this figure would exert a force on an electric charge at rest at the center. And yet, a charge at P does not experience any force. So, everyone says that, okay? What I will show now is that all of these people, they are wrong. All of these exercises that we all do as undergraduate and sometimes even in high school, they are wrong. That's a very strong statement, but you don't need to believe, but I will try to convince you about that. With experiments as well, not only with theory. Contrary to the opinion of these authors, there are two main reasons for the existence of an electric field outside resistive wires carrying a steady current. The first is the following. We know, if we apply boundary conditions to Maxwell's equations, that the longitudinal component of the electric field is continuous across an interface. So, if there is an electric field inside the resistive wire, and there must be, because if there is a current, there must be an electric field going against the resistance, otherwise there would be no steady current, because there is resistance in the wire. So if there is an electric field here, it must exist just outside. Okay? But usually people think that it is just in the outside, just at the border. I showed this is not the case. The second reason, suppose that I have a circuit here with a steady current, and at this specific point of the circuit, it points towards the x direction. Okay? By Ohm's law, there must be an electric field point towards the right, because at this point the current is going towards the right. But then I bend the circuit, and now at the same point, the current now goes up. The same circuit, I just changed it, steady current. So in this case, the electric field was pointing this direction. In this case, it is pointing in the upward direction. So the electric field is there. So the electric field has changed in these 2 points. What creates an electric field? Charges. Where are the charges which are creating the electric field all the way along the circuit? We never ask this question, but behind our mind, we believe that all the charges are inside the battery. Okay? Because there is where the electromotive force originates. So somehow, when I bend the wire, there is some change inside the battery, so that now, instead of the electric field points toward the right, it will point towards y, upwards. Okay? Somehow, it should have changed here. This is not the correct answer. So, the electric field at point C is not due to charge inside the battery. It is inside the battery, but other charges as well. Why? Because when I go from this situation to this one, if someone did change inside the battery, the electric field should change especially close to the battery at points A, B, E, or D. Not only far away, but at A, it continues in the same direction in both cases. At B, it continues in the same direction in both cases. At D, it points in this direction in both situations. At E, it points downwards in both situations. It did change only at C. So, it was not changed only inside the battery. Now, yes?
I'm trying to understand. Would it make sense to think about this wire, the geometry of the wire, as it like in terms of mechanics, as just a wall, and then having the battery be just a hose that has water going in some direction, and like the geometry of the wall will interact with the water and.
Yes, that's correct. And but in water we have the mechanical forces of the wall. In electrodynamics there are no these mechanical forces. So, but you are correct. That is the main essence of the explanation which I will give. So now I showed you everyone saying there is no force and so on, and I just showed you 2 reasons why there must be charge. Now comes the idea of Weber and Kirchhoff. They said that when we have a battery and a steady current flowing along the circuit, the battery creates a gradient of charge along the cross-section, along the periphery of the wire. It is positive close to the battery, goes to zero somewhere, and then it becomes more and more negative. And when I change, for instance, I bend the circuit, essentially what did change is the location of the nearby charges, which is different in this configuration and in this configuration. But these local charges are the responsible for the creation of the electric field inside the wire, not the faraway charge in the battery. Local charge spread along the surface of the wire. So this is the idea of Weber and Kirchhoff. So here I show you my whole presentation is already here in this slide. So instead of being neutral, the wire is charged along its surface for steady currents. It is positive close to the positive terminal, decreases the amount, goes to zero somewhere, and then becomes negative. These are the charges which create the electric field inside the wire. But then they also create an electric field outside the wire, which no textbook, very few textbooks mention about these electric fields. No magnetic fields, I'm talking electric fields here. So these ideas go back to Weber, 1852.
But is it a much weaker field because the air is not as good for propagating?
No, because of the continuity. I just talked about the continuity. The same order of magnitude inside the wire and outside, just the same. Just the same. So this is the subject of this book, which is circulating with you. How do we solve the problem? There are two ways to solve the problem. One, if I know, I can guess the distribution of these surface charges. And then this is the Coulomb potential, okay? And I can integrate that over the surface of the wire. So if I know the surface charge density, I can integrate that to obtain the potential and then the electric field by minus the gradient of the potential. Okay? But usually we don't know the distribution of surface charges. What we usually know is the potential along the wire. Because due to Ohm's law, for instance, the potential usually increases linearly with the distance. So we can apply Laplace's equations and give the boundary condition on the surface of the wire and at infinity. If we solve Laplace's equations, then we can we can calculate the surface charge distribution. So now I will present the results of these two kinds of calculations for different geometries. All of these geometries, each one of them is a chapter in this book, okay? Each one of them. The simplest one is the straight wire, which I was mentioning here. The first one to make this calculation was Wilhelm Weber, 1852. So we have a straight wire carrying a steady current, a resistive one. So Weber guessed that the distribution of surface charge was linear with the distance. And he then calculated the electric field inside the wire, which is constant. So he did obtain the constant electric field due to a linear gradient of surface charges. He didn't calculate the external one, but that simple one. When you do calculate, this is what we get. So inside the wire, we have a uniform electric field, Ohm's law, and outside the wire, there is this electric field. You see, it's positive, so it has a radial component here, which goes and goes there. The tangential component is continuous here and here. The The transverse component is not continuous because of the surface charge, and this is the calculation. Can we perform an experiment? Sure. This is an experiment which appears in a book by two German scientists, Bergman and Schaefer. Here they have a wire, and it is in oil, olive oil. And they do have, in this oil, they have semolina spread there. It's analogous with the experiment with iron fillings. But semolina does not does not react to a magnetic field. But if there is an electric field, each particle of semolina polarizes electrically. And so they polarize all of them, and we can see the lines of electric field. Analogous to iron fillings, which shows the lines of magnetic field. Okay? And these are the theoretical calculations according to Weber. And these are the experimental results of Bergman and Schaefer. This is another experiment made by Jeffimenko in the year in which I was born. So he gave me a gift as when I was born, okay? I just discovered that many years later, but that's a very nice experiment. So in this experiment, he's not measuring electric field, he is measuring equipotential lines. He fixes a point of reference, then he comes with a pointer, and this pointer he can measure. We do that in physics laboratories. So, and here he has a hollow conductor with conducting walls. So inside this air. So he can map the equipotentials inside the conductor and also outside. So these are his experimental line, 50 volts, 40 volts, 30 volts, and these are the theoretical calculations of Weber. So inside, these are the equipotential lines and the electric lines orthogonal to them. Okay? This is a different kind of experiment. He utilized currents 10 to minus 2 or 10 to minus 6 amperes. Okay? And he had a graphite paper and so on and so on and so on. This is another kind of calculation. This is a bidimensional calculation. Now the current flows in a strip, okay, bidimensional strip. So this is a paper which I published with this colleague of mine, Hernandez. The distribution of surface charge is linear with the longitudinal component, but in this direction it has this behavior here. And this is another kind of experiment. This is by Jeffimenko as well. Here we have a glass plate, and then he spread grass seeds. Okay, not semolina, but analogous. The grass seeds, if there is an electric field, each seed polarizes and then they align, just like strings. Okay, and this is above glass, and this is a conducting ink. Okay, which he painted above the glass, just like this glass here. He painted a bidimensional conductor, and then he spread grass seeds, and they align and they show the lines of electric field. Okay, this was published in the same year. In this experiment, it was 10 kilovolts, which he did make the experiments. This is another calculation, another chapter of this book. This is the transmission line. The current goes up and comes down, okay? So the solution will be the same. The main difference, so it will vary linearly with the distance here and here, the surface charge. The main difference is that along the periphery, the distribution of charge is no longer uniform, so it concentrates in the direction when they are close to one another, because they tend to concentrate here, positive and negative, positive here, negative here, and it goes decreasing the intensity, and so on. So this is the transmission line. this experiment with these transmission lines. The left one is by Bergman and Schaefer with this semolina in oil. Okay? The right one is the same with the glass by Jefimenko. He did paint a transmission line here with conducting ink, and then he spread the grass seeds here. And then we can see that inside the conductor, the grass seeds, they are parallel to the direction of the transmission lines, but there is an electric field here because the charge, they are positive here, 0, and then negative here. So the electric fields come from the positive to the negative. But you see, and here are the theoretical calculations superimposed on the grass seeds. It's remarkable. The fitting, to me, is nothing to be desired. Okay? The same as here. Third case, a coaxial cable. So we have a battery here, the current goes here and comes back from in the external conductor. So we usually in physics we utilize this system because the current goes in and comes back in the return conductor. The magnetic field goes to the right hand rule, but when the current comes back, also it is spread, it is the same intensity, so it cancels the magnetic field. So outside the coaxial cable there is no magnetic field, but there is an electric field, which almost no author mentions that. Very few of them. In particular, this case was considered by Sommerfeld, the calculation of the electric field, but he did calculate only in the region between the two conductors. He didn't calculate it in the outside because in his system, I believe, either he utilized the superconductor here or it went to infinity, the larger C, A, B, and C. Either he made C go to infinity, I don't remember, or he utilized the superconductor here. So in his case, there was no electric field in the outside. But Sommerfeld did calculate the electric field in the region between the two conductors. He didn't mention Weber, he didn't know about Weber, but he knew about the solution. Another very interesting case, a solenoid. This problem, he was considered by Held. Held is one of the authors of one of books on electrodynamics, one of the very few authors of classical electrodynamics who know about these surface charges. So this is the cross-section of the infinite solenoid. Okay, the solenoid is here. So the current goes like that. So the magnetic field is uniform in this direction and 0 in the outside. Okay, the magnetic field is there and 0 magnetic field. But what I'm showing here are the lines of electric field. This is just similar to the situation, but this is a wire. In Held, it is an infinite solenoid. But I want to show you two things. The first case, there is, in the case of the magnetic field, there is a uniform magnetic field inside, no magnetic field in the outside. As regards the electric field, there is electric field inside and outside. In both situations, both regions, there is an electric field. And moreover, we can obtain an analytical solution for this case. And in particular, when we calculate the density of surface charges, it is no longer linear with the angle here. The potential goes linear with the angle, but the density of surface charges, it goes with the tangent of the angle. Okay? So it goes to infinity when we reach the battery. Okay? In this region, it is linear with the angle, with this angle here. But when we go in this point, it's no longer linear with the angle. It grows faster than linearly, okay? In the linear conductor, the density of surface charge is linear with the longitudinal variable. In this curved geometry, the potential is linear with the angle. It decreases linearly from V over 2, 0 minus V over 2, linear with the angle. But the density of surface charge is not linear. But we have analytical solution. Okay?
This computation was done using Weber's electrodynamics.
No, this is standard electrodynamics. Yes, standard electrodynamics. And this held. He also made the calculation when the solenoid is here, it is superconductor here, and there is resistance only in one small region, then superconductor. Just like when we draw a circuit, that we have a resistor and then connect the wire. So the resistance is concentrated in this region. So this is his analytical, in this case, numerical solution by Held. Now I will present a calculation of myself, okay? Which I did publish with this Hernandez in 2003 in Physical Review. We did calculate the solution for a ring, a torus, as the mathematicians like, okay? A torus here. So we have a torus with a battery here, and the current goes like that. So just steady current, okay? And the current goes like that. So, this, my quote, he was my student. At that time, I believe he was my PhD student. Nowadays, he is a professor in another university. But at that time, he was my PhD student here. So, we did publish that 17 years ago. So, it is a ring with steady current, okay? No waves, nothing, just steady current. So there is a battery and the current comes like that. How do we solve the problem? We solve it solving Laplace's equation. Okay? Laplace's equations. However, we need to utilize toroidal coordinates. I won't go into the details here. I don't even remember them as well. But these toroidal coordinates, because this Laplace equation, it's not separable in toroidal coordinates. Laplace equation is separable only in 13 systems, rectangulars, spherical, and so on, but not in toroidal coordinates. But there is a method which is called method of R separation, in which we separate square root of a certain function and then multiplied by 3 separable functions. Okay, this method is well known in physics. Okay, and these are the toroidal coordinates. Then how do we solve the problem? So we apply Laplace equations in the outside and apply the boundary conditions that the potential goes linearly along the ring. Okay, and that it goes to 0 at infinity. And then we find the potential everywhere in space, and from that we calculate the surface charges. Okay? So we give the potential that it varies linearly along the ring. So this is the analytical solution which we could find. It's amazing, but we could find the solution. But it's very, very complicated because it's based on 2 infinite summations of a Legendre functions of the argument of the Legendre function is an hyperbolic cosine of a toroidal coordinate. So forget to understand about that. You cannot understand that because it is 2 infinite series going from 0 to infinity of an Legendre function of an hyperbolic cosine of a toroidal variable. Very complicated. But we could find the analytical solution. And then this student, I don't work with computers, but this student of mine could go to Mathematica, and then he could see how it looks like this solution, okay? So, this is the analytical solution of these hyperbolic cosines of infinite series and so on. And here we superimpose that on an experiment by Jefimenko. So you see here, here I'm plotting the equipotential lines, okay? And the experiment shows the lines of electric field, because the grass seeds, they follow the lines of the electric field. So they are just orthogonal to one another. These are analytical solutions. And these are the experimental results by Jefimenko. Okay? And this is the calculated surface charge distribution.
Your calculation is according to Weber's electrodynamics.
Sorry?
Your computation.
Laplace equation, just that.
But you know, but you use this, how to say this, idea of Weber.
The idea of Weber was about the surface charges.
I see. And the previous one, the solenoid, did also use that idea? Was surface charges.
Yes, all of them surface charges. At the top here, I am showing the numerical solution of the ring. So the charges go linearly when we are far away from the battery. If the battery is here at the left, so the potential goes linearly with the angle from here to there. But the surface charge doesn't go linearly. It goes linearly here, but then it explodes close to the battery. This is the analytical solution based on this solution here. But when I was in Hamburg, I could finally read Weber's papers, because before I didn't know German and so on. Then when I got the invitation, I went there. Then I read Weber's, most of his papers, 6 volumes, this size, each one. I read most of his papers. And then I just found a remarkable paper by Weber, 1852. And in this paper, Weber calculated 1852. He did calculate the surface charges for a straight conductor carrying a steady current with the charge going linearly with the longitudinal component. And he also did calculate the ring, but he didn't calculate exactly the ring as we did here. But he made a very fascinating approximation to perform his calculations with a linear conductor. I discussed that in the appendix of this book. How he did do this calculation. He did calculate only approximately, but he arrived at a remarkable conclusion. 1852. I will read here his words in this paper. What he said. So this is the analytical calculations which we did. Weber, in this paper 1852, the electric charge of the circuit increases from the neutral point, far away from the battery, towards the battery, and not uniformly, but accelerates gradually. Not accelerating speed, accelerating the amount of increasing. So to me, this guy is just remarkable, this Wilhelm Weber, one of my heroes. Okay? Now, can we measure the force? Because up to now I'm talking about equipotential lines and fields of electric field. Okay? But can we measure the force? Yes, we can measure the force. This is an experiment by Sainsbury. Published in Review of Scientific Instruments in 19 85, he has a torsion balance here, and he has a circuit here which will flow 1 kiloamp. Okay? And so this is a torsion balance. So there is no current. Then he charges one extremity of the torsion balance. When he charges it, immediately it is attracted towards the wire because of image charges. Even without current in the conductor, when you put a charge here, you induce opposite charges here, and it will attract. So the vein comes from there to here. No current here, okay? Then he passes a steady current. Depending on the direction of the current and so on, the vein comes in this direction or in this, an extra component, which is proportional to this current. So he could measure the forces of 10 to minus 7 newtons with a current of 1 kiloamps and charging. The charge here was 10 to minus 10 coulombs. And this is exactly the amount of force when we calculate with the expression that we get. Okay? So we can even measure directly the force. But now I can ask, do these surface charges here, this is from Weber. Can we really measure them, the surface charges? Yes, we can collect them. I'll show another kind of experiment. Unfortunately, I'm not an experimentalist myself, otherwise I would try to do them. But I quote some of them. This is an experiment by Shabai and Sherwood, 2 Americans. So they have here ground, 2 batteries, and they have 4 resistors. And to collect the charge, they utilize a very simple device which we utilize in electrostatics. We have here a mylar strip. Mylar is an insulator, but it is metallized, so they like a aluminum foil on the top of it, and you hold it with an insulator. Okay, so you come close with, so it's a metal, a flexible wire, and you hold it with an insulating handle. Okay, when you get close, if there is an electric field here or this charge, they will attract the mylar strip, and when you get in touch, it will acquire charge of the same sign, and then it will be repelled. We do that in electrostatics all the day, every day. And then you just test this charge with an electrometer to see if it is positive, negative, and the amount of charge. And this is his drawing in this book. And this is the result of his experiment. So this uniformly negatively charged up to here, then the amount of density of surface charge decreases, it goes to 0 somewhere, then it begins to become positive, and then becomes more positive here. This is a real collection of charges. Okay, he collected those surface charges. This Shabai, and he has even videos that you can see in the extra material of this textbook, okay, of these experiments. A colleague of mine in Germany, Hermann Hertel, he has also some videos in which he shows something being attracted and repelled and so on and so on and so on. So, conclusion. There are charges spread on the surface of a resistive wire carrying a steady current. The surface charge density is constant in time, but varies along the length of the wire. It's positive, close to the positive terminal of the battery, goes to 0 somewhere, and is negative, close to the negative terminal of the battery. The surface charge density varies linearly with the distance along a straight wire. However, for a bent or curved wire, it does not vary linearly with the angle. The potential varies linearly, but not the surface charges. These surface charges generate not only the internal electric field responsible for Ohm's law, but also an external electric field at all points in space, not just at the vicinity of the conductor, everywhere in space. So all these problems here, they are wrong. Because if you put a stationary charge here, there will be a force act on it. If you put a stationary charge at the center of the circle, it goes down or up, depending on the sign of the charge. I showed to you that the electric field, it is positive here, 0, negative, and negative. So the electric field comes like that. So if you have a positive charge, it will go down. If you have a negative charge, it will go up. Even at the center. The battery breaks the symmetry. Okay? All exercises that we do, they are wrong. All of them. Therefore, a resistive wire carrying a steady current exerts a real force on an external charge at rest relative to the circuit. These facts were first calculated by Wilhelm Weber 150 years ago. Also, his pioneering work has been totally neglected. So, the conclusion. These are the surface charges which create the internal electric field, but also an external electric field. But Weber got there first, not myself. Okay, thank you.
You have any questions?
Question and comment. The question is the following. This was something that always puzzled me, related exactly to the situation. You have a straight wire with a current,
Yes?
and now you put a particle with a velocity parallel to the wire, and there appears according to Lorentz, appears a force towards the wire, right? And then, but then, if you change the coordinates, as we do in mathematics, now the Galilean frame that follows the charge, uniform velocity. So the charge is at rest, has uniform velocity, with respect to this coordinate.
Yes?
So does the force disappears? This is discussed in Feynman's book.
I know.
And there he says,
Every book on relativity discusses this problem.
he says that there's this relation. Well, then you have
Transformation of the
exactly.
field.
Then you have this, since you're in a reference frame that moves related to the field, then you see and the electrons are moving and the positive ions are not moving, then some of them shrink,
Yes.
shrink in space, and then the density of charges change, and then an electric field
Yes,
appears.
I know.
It computes the electric field and gives you the same force. So you have an electric field instead of a magnetic field.
In this
magnetic
different
force,
reference
magnetic
frame.
Force instead of a magnetic force. If you have this, but how do you comment on this explanation? Because it's more or less related to what you're saying, right? Here, another question. Do you still have a magnetic force?
Yes, sure.
Because you have the electric plus a magnetic.
Yes, sure. But this calculation of Feynman appears in every textbook. But you see, what happens when you put V equals to 0?
Yes.
Equals to 0, the magnetic component.
Zero. But the force electric is.
No, if you go to that frame, in that frame the charge will be moving. And if you do the calculation, the electric force would go to 0 in that frame as well.
The question that in all of these calculations, you have this 0 at the middle of the wire. But can you also do this mathematical idealization that have an infinite wire?
Yes, you can, but the problem is that what defines the 0? Where is the charge 0? It's not arbitrary, it is the battery. It is the battery who says where is the 0.
You must have that.
Yes, you must have that battery, because even for an infinite wire, as it has resistance, it must have a battery somewhere. we usually we don't draw the battery in this case. In this case, we usually draw it, but it must be somewhere. Otherwise, there would be no current in a resistive wire. But you need to have the battery somewhere, even if you put it at infinity, but it must be there.
Why do people, like you said, they said there were no evidence of forces on the static charges? Because you said they exist, right?
Yes, but maybe at that time, no one that had done these experiments. Maybe. Yeah, I'm just showing here many different kinds of experiments. They are. I'm showing here some from 1950 onwards.
Did Ampere see any of that?
Ampere? Ampere 9, no. He came 20 years before Weber.
Yes, but he never saw any of those.
No. Ampere. No.
It's a different type of experiment because we talk about charge. And Ampere
It was always with current, interacting with another current.
Yes, so he never looked at charge.
No.
Never looked at
Yeah.
Yes. And then there's not such problem in Ampere's electrodynamics to think about. Because the unification of electric charge moving with current elements it was Weber that made. If you have a current made by induction,
Yes.
how it work in this?
It's a different, though. We need to make the calculations.
But there are charges.
Not necessarily. Not necessarily. Weber did consider this problem. For instance, if I have a ring without any battery, and then I can approach a magnet
Yes.
from the right or from below, for instance, we say uniform velocity and so on. Then we will induce a current here. But in this case, there are no batteries, so it will not be the gradient of charge which will cause this electric field, but will be the magnet which will exert the force, which will go against resistance. So in this case, it's not surface charge. Surface charge is when we have a battery, but not when we have, for instance, a magnet moving towards a ring.
Question: is this Weber electrodynamics consistent or compatible with pure relativity?
No, not at all. But it is completely compatible with Maxwell's equations. And Maxwell showed that in the last chapter of the treatise. But it is totally against relativity. Totally against. Because it goes against Lorentz force law. And
Is it not strange that because also
Yes, of course it
relativity
is.
was tested,
yes, but then you see what Maxwell said of Weber. I quoted yesterday that with Weber's electrodynamics you deduce all known facts of Faraday's law of induction, Ampere's law, and so on. Literally said so by Maxwell in the last chapter of the treatise.
Just an answer to the other question. When Lorentz made his form, it became the problem of the charge moving. He had to create another set of equations that we call Lorentz transformation. In Weber's electrodynamics, the velocity and acceleration are relational.
Relative to the interacting charge.
Then we don't need to
For instance, this
Lorentz
problem,
transformer to get the same results. Experimental
this
results.
problem that you mentioned, that here we see a magnetic force, but if you move together with the charge at rest, so there is no magnetic force, there should be no force. This problem doesn't appear in Weber's electrodynamics, because in Weber's electrodynamics there are no components of force which depend on the observer. This kind of problem only appears in relativity, but not in Weber's electrodynamics. This is what attracted me to work with Weber. Yes, please?
So, but how do you reconcile relativity?
I don't reconcile. I'm against relativity. I'm fighting against it. I hope some of you will help me in this fight, because now I'm alone For 30 years, I am alone fighting against relativity.
Not alone, not alone.
Not alone, yeah. John Paul is here. John Paul is here. Not alone, just making joke. There are people also somewhere else fighting, but I don't want to reconcile. I want to finish with relativity, really.
But what about the experiments then?
Yes, I'm trying to show here.
Okay.
There is another experiment when you come out of the room, you can see also that.
I already proposed several. Yesterday I talked about the spherical shell.
Yeah.
There are people trying to do it in Ukraine, in Germany, in USA. I hope some of them will succeed.
But
My
even
lifetime.
general relativity?
So even this E equals to mc squared, because people know, when they do those nuclear reactions, for instance, right, they transform mass into energy, I believe, right? How do you explain that? Because we see, we have bombs, we have everything.
Yes. I will talk tomorrow about something related to this subject, which Weber did as well, which is called the Weber's planetary model of the atom. So that will be the subject for tomorrow, so I'm not answering today.
Okay, so tomorrow will be the Weber. Tomorrow will be the Weber bomb.
Tomorrow, if you are not here, later on you can give a look.
Okay, so let's thank the speaker.